All right, so we were talking about the Hamilton standard, the hydromatic propeller, and I stole a bunch of stuff off the internet today, and I'm pretty happy about that. So I'm going to go through this again, just a quick review using the stuff that I stole off the internet. But I do have to remind you that one of the things that I mentioned was that there are variations of this propeller. Not only were there variations of, well, there's just the constant speed version, and there's constant speed feathering reversing, but also I have noticed that the way they actually operate varies depending on the particular model. And so I had us working with a double acting governor, and I think I'm going to go away from that, and just for simplicity reasons. And I kind of told you that, but my photos that I had originally were very much geared towards a double acting governor, which was this. And I did make a note up here, which I just took from down here. Oil to the backside, inboard side of the piston decreases the pitch. And so this is they're underspeeding right here, so we have to decrease the pitch. And so it was pressure back here. And then I added this one, oil to the front side or the outboard side increases pitch. And that's what it says down here. And that's what they're up to up there. Increases pitch. Yep, because they're going too fast. So, and then there was the on-speed condition. And I think I'm going to get away from those, and I'm going to go more towards these newer slides that I picked up because I really like them. They're easier and to see and read. And if we look at this one right here, just the basic propeller, you're going to see it's the same design. There's nothing's really changed about the picture. But what I do love about this one is here's the transfer valve in here. And I'm going to show you, hopefully I think I have some pictures that will show it, but this little pilot valve inside of here moves. So under normal operating conditions, well, it's going to be pretty hard to pick this one up exactly, but oil would come in and it finds its way up and through, and it goes a different way. Yeah, you can't really tell on this. I was going to actually take some time and color it in, but I think I have another one. But anyway, so the pilot valve here is what moves when it gets under pressure. But you can see the gears right here. You can see the distributor valve that we're talking about right in here. What else is there? Well, that's all the stuff you need to know about right there. The governor's attached up over here. I thought this was kind of cool. Nice picture of the hub assembly in there. Excuse me, the distributor valve again, but pulled out this time, so you can take a look at it. I'll probably use more pictures like this next time. I did love this one because it really showed a good picture of these rotating, or the cams, the inner and the outer cams. It doesn't really explain how they work. I did find a little video that was like 30 seconds and I forgot to save it. So distributor valve plugged in there. It's not important. Just the assembly. All right, here's the stuff that I thought was kind of cool and important. And so if we take a minute to look at these as a review, remember that this item right here is what's attached to the blade. So 3 forces control the propeller blade angle on this one. So centrifugal twist, which we've always known about. Engine oil under pressure is supplied by the engine oil pump. So it's centrifugal twisting force and just engine pressure, which is just your 60, 70 PSI from the oil pump off the engine. So these two, 1 and 2, work together. Centrifugal twisting movement, which tends to move the blades towards low pitch, and engine oil pressure supplied by the engine pump, which supplements centrifugal twisting force. So engine oil pressure is low pitch. So notice this. Engine oil pressure comes in here, it fills here, it pushes the piston back, and when the piston goes backwards, it goes into a low pitch, which is kind of funny because, oops, too far. Well, I screwed that all up. Don't know how to manage that. Hang on a second. Please stand by. I think my slide just got out of order. Or I went through them too fast and it screwed them up, which I notice it's been doing. Oh yeah, this is what I wanted to go to. All right, so let me switch back and forth real quick. So here, from current slide. Okay, so I said piston going back is engine oil pressure, That's supplementing centrifugal twist force, which goes to a low pitch, right? You got that? Low pitch. Low pitch, outboard. I'm gonna have to go back to these. Low pitch, outboard. Whoa, look at that. Oil to the backside decreases pitch. Oil to this side increases pitch. This is working the complete opposite the way they have the distributor valve set up in this one. And the cams, I shouldn't say distributor, the cams. It's kind of weird, you know, and I can't really explain to you why this particular model or this drawing chose to do it this way, but hey, so be it. It is what it is, right? So trust me, I'll never ask you to remember an inboard, outboard, just worth noting. Oil on one side does one thing, oil on the other side does something else, but you should understand that centrifugal twisting force and engine oil under pressure fill up this area, push the piston back, goes to low pitch. If you want to go to high pitch, drain off the engine oil from this way, let it drip out, and put governor pressure back here to overcome centrifugal twist and move it forward. So I think I'm going to start teaching it more like this because this, I think it's a more simplistic way of doing things. And it matches what we've learned so far, kind of cements that in. So, oh yeah, this is what I was thinking about. So, so same thing in an underspeed condition, I haven't really read these slides, I just put them in here. So underspeed condition, we know that underspeed is going too slow. We've got a decreased pitch. So decreased pitch, engine oil pressure here, release the governor pressure, to go back through the distributor valve and drain out. And then we have engine oil pressure is going to come through the distributor valve, fill up here, go to low pitch. If you're in an overspeed, the opposite, drain off the engine oil, add governor pressure here. So you have governor pressure coming in off the governor, engine oil pressure, high pressure off the governor, through the pilot valve, through the distributor valve right there and off into here. And then we go into increase the pitch. On speed, of course, you just block everything off so nothing goes anywhere, holds it put, holds it. Okay, so feathering, nothing's changed here. So in the feathering mode, we are going to run the feather pump. So we're going to push the button in, the holding coil is going to hold it. An electric motor is going to boost the pressure. You can see it's here represented by green. So I think 6 is the inlet right here. So boost pressure comes through, hydraulically isolates out the governor. So it bypasses the governor and stops the governor from doing anything. It moves this pilot valve so that it's pointless now. So boost, the feathering pump comes up through. It comes into where it's normally governor pressure. So normally this green is just red governor pressure. Nothing has changed. Makes a little loop here through the distributor valve. Comes in here and it just pushes this all the way forward going into feather as it drains off this oil. All right, so then it goes all the way into feather and then it's held there by aerodynamic forces, or we could say it goes into feather. The feathering pump builds up to over 650 PSI. At 650 PSI, the holding coil cuts out, releases the button, shuts off the motor, and aerodynamic forces hold the blades into the feather position. Then I want to unfeather it. So here we go. So unfeather it. I almost need to do these two side by side so you can see something. All right. Note so unfeather it. So we push in the button and we hold it. I'll go back and forth. Oops, wrong way. All right, so now high pressure over 650 PSI probably is gonna come in, again, same thing, go through the distributor valve, but it's gonna build up and pressure on the back side of this valve right here and push it forward. As back here, notice this valve is back here. And so the pathway is, it comes and it's allowed to press here, but does nothing. Pathways, it comes here and around that way. Let me see if I can do it fast enough here. And this way, it would have came here and around this way, but it doesn't. That was the old path. This way, around, old path. But now it gets a new path. this way, down, over, and up. And if we look back here, this before was the yellow coming up and in and around, but not anymore. So it just realigns everything. So green is going to this side, but when I unfeather, now the pressure goes to this side. So the distributor valve just realigns it. So where this used to be engine oil pressure only is now boost pump. It is unfeathering pump pressure, 650 to 700 PSI going this way, driving it back. But as soon as it gets a little ways, you're going to get some angle to the blade. The wind's going to pick it up and it's going to just start rotating on its own. And then you can release the button and the governor's going to work. It's going to say it's in an underspeed condition, drive it to low pitch. And that's how that works. Yay.
Question, Kevin.
Yes.
So the reason you can use the engine oil pressure instead of a governor is because of the centrifugal twisting force.
Yes, is aiding it.
Yeah, so because that's aiding it, you don't need as much PSI as if like you need the governor for it.
Right. That's why going back here, why governor pressure is on this side, the back side, and not on the front side, because the back side has to fight centrifugal force to go forward, but going backwards, you have engine oil plus centrifugal force is enough.
Okay, sounds good.
All right. All right, that was all my new photos right there, I think. Yes, it was. All right, so let's go here, and I will write some notes for you about unfeathering. Unfeathering. So what happens? Well, the feather button is pushed. Feather button is pushed in and held, pushed in and held by the pilot. And I'll put this, since it has to be held by the pilot, since holding coil would just release it. Holding coil would just release it. So at this point, the prop's in feather. So the pilot pushes in the feather button and lets go. Well, the feather button's going to go in. It's going to start the pump. The pump's going to run. It's going to hit 650 PSI within a second because the prop's already on its stops and just shut down, right? So remember, you've got to push it in. You got to push it in and hold it so that the feathering pump continues to run and builds up over 650 PSI and transfers the distributor valve. So feathering pump will run and build up pressure build up pressure beyond 650 PSI. All right, and because the button is held in, because button is held in, the cutoff will not stop motor, electric motor, and pressure builds to about, I think it's about 700 PSI. All right, I'll call it extreme pressure. This extreme pressure will cause the distributor valve to shift and reverse the normal oil flow. Extreme pressure will, let me see, will cause the distributor valve to shift and reverse normal flow. Valve to shift and reverse normal flow of oil. There we go. Then high pressure oil is then directed to the opposite side of the piston. So high pressure oil is then directed to the opposite side of the piston. And unfeathers the prop, and unfeathers the prop.
What is the timetable on this action happening, going from unfeathered to feathered and then from feathered to unfeathered?
The prop that we have in the lab is really slow, but that's just because it's the size of the pump that it's actually running off the mule. So it's pretty fast. I was trying to think, maybe once you hit the button and start to hold it in, probably 2 seconds, 3 seconds, I think, before you start to get some windmilling action, and then you can start release it.
Oh, wow. Okay.
Yeah. These things move pretty dang fast. When prop starts to windmill, release the feather button. Release the feather button. Release the feather button, and prop will return to normal operation. And prop will return to normal operation. And then I think the last point, I made it a subpoint, don't know why. Distributor valve will bleed off pressure, in excess of 750 PSI. In other words, you just can't have pressure built up in there and have nowhere to go with it. It would be a bad thing. So you still have to have some sort of bleed off in there, and you can see it, I think, in this picture. Let me pull up this one. I love how I pull up a picture, but it doesn't follow suit. Oh, sorry. I saw it right there. Right there, number 21. I wish I had the rest of this. I may actually have this book somewhere in my office that has these pictures. I just had to stay off the internet, but I believe 21 right there is your pressure relief valve. And so if you get anything above 750, it's right in this area right here, and it'll bleed it off. Oh. All right. I think that's all I really have to say about this prop. So you guys want to watch an old-timey movie? It's about a half an hour.
Let's go.
All right. I enjoy it. It's got some cool stuff in it, and I appreciate the fact.
Just one of those without sound?
No, it's got sound. Let me see. Share computer sound. Didn't have sound.
That'd be real old time.
So here we go.
Is it just me or is it all just static?
It's all static right now. You have to read the words. And you should probably appreciate how hard this was state-of-the-art filmography or whatever you call it at the time.
Read. That's too much for Steven.
The three main assemblies of the de Havilland hydromatic air screw are the barrel and blade assembly, the distributor valve housing with its oil conductor sleeve, and the dome assembly, which are assembled in that order. In many installations, the constant speed unit is fitted to the engine crankcase immediately behind the air screw and is driven by a quill shaft. A special gasket is used between the crankcase and the constant speed unit, and no other jointing must be used. The nuts securing the constant speed unit are tightened down evenly and firmly before connecting the pilot's control. With the barrel and blade assembly slung, carefully clean off the splines on the air screw shaft and in the bore of the spider. See that the rear cone is in position and undamaged.
Rear cone. See it? It's the rear cone.
Insert the oil conductor sleeve, using the extractor as a convenient handle. Note particularly that the oil conductor sleeve is an air screw part. Lightly smear the splines of the air screw shaft with anti-seizing compound. When offering up the air screw, great care should be taken to get both sets of splines in alignment. No undue force should be used, and when the shaft has entered, the air screw should slide smoothly into position. Next, insert the front cone oil seal washer. Then the front cone oil seal between the air screw shaft and the spider, shaped to fit the bottom of its groove, taking great care that it is kept square with the shaft. Take great care that no damage is done to the feather edges of the oil seal. Now turn the blades in the barrel to move the gears aside. Assemble the split cone around the flange of the air screw nut and screw them into position on the air screw shaft. A strong tube spanner is used to tighten this nut, and the leverage is applied through a short tongue with extension tubes. A torque of between 750 and 900 pounds-feet is required, and as it is difficult to obtain this torque without an unwieldy length of lever, the nut is jerked up as far as possible. And finally, with the load still on the tommy bar, one or two smart raps are given to the tommy bar with a lead hammer, to ensure that the air screw is full tight in position. Fit the snap ring into its groove. The distributor valve housing joint washer is now smeared with grease and inserted in the air screw shaft where oil conductor sleeve. Marking paint is then smoothed over the joint face of the distributor valve housing. The housing is then screwed into position in the air screw shaft to ascertain if the housing is bearing evenly on the copper joint washer. Note that for screwing up, the housing is turned in an anti-clockwise direction. If, on removing the housing, the marking is unsatisfactory, and it is felt that the housing is not pulling hard down upon the washer, a second washer may be added to make the joint effective. The distributor valve housing should be put up with a torque not exceeding 100 pounds-feet. It was seen that whereas the air screw nut was screwed up in a clockwise direction, the distributor valve housing was screwed up in an anti-clockwise direction because it has a left-hand thread at its inner end. An effective lock is made possible, therefore, by employing a single lock wire whose tang engages both components. It will be seen that the tang is thickened up to fit both the castellations in the air screw nut and the locking grooves in the distributor valve housing. Before mounting the dome, it is essential to turn all blades into the full. Though it is possible to turn the blades by hand, a better control is had by using a torque bar. There is then less risk of damage to the segment teeth. The full feathered position is obtained when the end teeth of the gear segments are felt to encounter the stops in the barrel support blocks. On non-feathering air screws, the blades are adjusted to the degree markings on the barrel around the blade aperture. The oil seal rings on the distributor valve housing require attention. These should be liberally oiled. After rotating the rings to ensure that oil reaches the groove, see that the ring gaps are not in line. Before installing the dome, it is most important to see that the stop lugs on the rotating cam are in contact with the coarse pitch stops on the stop ring. This is evidence that the piston is back as far as possible in the dome and that the cams are in their full feathered position. The dome barrel oil seal is now stretched into position around the fixed cam base with the feathered edge away from the dome. Now remove the dome plug from the dome assembly and insert the special handling bar. The handling bar enables the assembly to be lifted about its center of gravity. Having noted the assembly position from the markings on the dowels and the markings on the dowel holes, offer up the dome assembly. Should the dowel holes in the fixed cam base not engage the dowels in the barrel shelf, the whole dome assembly should be turned through a full revolution in the direction of air screw rotation. This is most important. Now engage the dome retaining nut. This nut has not only to secure the dome, but it also has to carry the load arising from the preload on the gears and the compression of the dome barrel oil seal. The necessary torque is applied with a special spanner. The dome securing nut is locked by means of a grub screw. This in turn is wired to prevent its unscrewing. Before operating the air screw under pressure, the blades should be turned by hand to the fine pitch position as a check that the dome has been correctly installed. For this check, the use of torque bars is most essential. The movement of the blades can be observed against the degree markings stamped on the barrel at the blade apertures and should agree within a small margin. It will be immediately apparent should the pitch operating mechanism have been incorrectly meshed, as one tooth displacement on the smaller size air screw will produce an error of about 8 degrees, and on the larger size, one of about 10.5 degrees. Finally, the dome plug is inserted. This is tightened down onto its oil seal, unlocked by means of a lock wire. The de Havilland hydromatic air screw owes much of its reliability to the careful manufacture of its individual parts. These are produced in one of the most highly specialized branches of the aircraft industry by the skillful use of elaborate tools. Aircraftsmen should maintain the same high standard of craftsmanship when installing it for use.
But wait, there's more.
How do they mill those parts with a machine?
After the installation of the de Havilland hydromatic air screw, the aircraft should be wheeled out for engine running and air screw adjustments. For engine starting and for air screw testing, the use of auxiliary storage batteries is essential. By relieving the aircraft batteries of the heavy loads imposed by air screw testing, they preserve the proper aircraft voltage which certain of the instruments require. Before commencing to check the air screw for adjustment and operation under power, the air screw control lever is put to the maximum RPM position and the engine started up. RPM to warm up. The air screw lever is then drawn back to the minimum RPM position and left until the revolutions cease to fall. This indicates that the air screw dome has filled with oil. The air screw control lever is then pushed forward and exercised over its entire range to ensure that all the air has been replaced by oil. This condition is indicated when the RPM follows the movement of the control lever. The air screw control lever is then pushed fully forward into the maximum RPM position, and the throttle opened up to the takeoff boost as specified on the engine data plate. The RPM should remain at the maximum permissible, in this case 3,000. Opportunity should be taken at this time to note the amount of overswing and the time taken for recovery. Normal overswing is about 100 RPM. Similarly, when the throttle is brought back, the underswing of the needle should be noted. Its amplitude should be of the same order and should rapidly subside. Finally, the constant speed lever is brought back to the minimum RPM position. During this movement, the RPM indicator needle should follow the constant speed lever closely until the minimum RPM governing is reached. On this installation, this is at about 2,000 RPM and should occur when the constant speed lever is at the end of its quadrant. If the air screw is being adjusted to the engine for the first time, it will often be found that the maximum obtainable RPM is either more or less than the maximum permissible. Adjustments then have to be made at the constant speed governor, which is fitted with stops to restrict the maximum RPM as required. Behind the protecting cover on the mechanically operated governor will be found the maximum RPM stop, a cheese-headed screw with a locking nut. When the RPM is found to exceed the maximum permissible, the procedure for adjustment is as follows. With the constant speed lever fully forward, the engine is opened up to takeoff boost. Then the constant speed lever is drawn back until the required RPM is shown. The position of the control lever in the quadrant is now marked and the engine stopped. The maximum RPM stop is now unlocked and screwed in until it is just felt to make contact with the stop arm on the speed control shaft. Adjustment is then made to bring the air screw lever to the takeoff position in its quadrant. When the governed RPM is found to be less than the maximum permissible, first unscrew the stop one turn and run up the engine to ascertain what increase of RPM is affected by a single turn of the stop. The stop can then be turned the required amount to complete the adjustment. The controls are then adjusted so that the control shaft lever just makes contact with the stop, with the air screw lever in the maximum RPM position. Large multiple-engined aircraft are often provided with hydraulic control to their constant speed units. Adjustment is more easily effected in these installations, since it is required merely to screw up the cover one turn and to note the corresponding decrease in RPM. The necessary adjustment, clockwise or in this case anti-clockwise, is then made to obtain the correct maximum RPM. The cover must of course be locked. With the engine opened up to about 1000 RPM, the feathering switch is given a firm, deliberate pressure. As the blades turn into the feathering position, the RPM will drop to about 500 or 600 by the time the operation is complete. After approximately 10 seconds, the feathering button will throw out, indicating that the air screw has feathered. The engine should then be stopped by switching off in order to verify that the blades have reached the full feathered position. To unfeather, the pilot's feathering switch is again depressed and held in the closed position until the blades are seen to have resumed a normal flying angle. Subsequently, the air screw may be unfeathered with the engine running. To do this, hold in the feathering switch until the RPM rises to 800 and let go. Where the engine is permitted to run, it will occasionally be found that the air screw commences to unfeather soon after reaching the feathered position without the pilot's switch being operated. This action is not abnormal. It occurs by reason that engine oil pressure is still acting within the dome after the feathering pressure has been cut off. This cannot occur in flight, as a feathered air screw will stop the engine even though the throttle be left open and the switch left on.
Do you like that?
That was a pretty neat video.
Hey, you guys just had a 30-minute nap. What are you lying about? All right.
Anti-clockwise.
All right. So 420, give me 1 minute here. So in the past, I've had enough time where I get into a little bit more of the PT6 operation. I'm probably just going to, I'm deleting it for sure now. I'll probably delete it from the class because it's really more about PT6s and stuff. And I talk about the prop. Really, the prop on this thing is just the Hamilton standard steel hub. So it's not a big deal. It's a very complicated system, and then it uses 3 different governors and to control it. But having had Phil's class, there's certain things you guys should understand and even be able to explain back to me, like the blades on this King Air are all feathered. And I've told you don't feather it on the ground, but yet on a King Air with a turbine, it is feathered. Anybody tell me why that's not a big deal? Or even why you would want to feather it on the ground?
It's a free turbine.
Okay, so hey, we got a free turbine, which is not connected to the starter. So that is correct. So free turbine, not connected to the starter. So it really doesn't matter they're in feather. And if you didn't feather them, then the front half of the turbine there would continue to rotate for a long time once the oil pump is shut down. That's really bad for the bearings. So you actually want to feather it to shut down both sides of the turbine. So that's not even a real picture. I figured that out after I found on the internet. That's just Microsoft. And then I kind of got into some of the governors on here. The thing that I didn't write a whole lot about, and I don't remember where I did put notes, but remember that especially on an aircraft like this, it does have a beta range, and beta range is from 0 pitch going backwards. So you can back up the airplane. It's not really used to back up the airplane. I mean, it can be, but it's used to slow the aircraft down upon landing. And there's almost always a switch that is integrated into the landing gear. So you have to have weight on wheels, sometimes called the wow switch, weight on wheels, or I prefer to call it a squat switch, because when the weight is on the wheel, it squats down a little bit on the struts. And then there's a switch that will often, like here on the scissors or back here in the main landing gear, that engages when the weight is actually on. So you have to have a weight on the wheels, and then it unlocks a gate that allows the pilot to take the controls, the prop controls, past into this range back here, which is reversing. And then on aircraft that do have reversing propellers, the prop control levers actually act like throttle levers once they go into that beta range. So you bring the prop lever controls back into beta, it's going to go at a flat pitch. And then the more you pull it back, the more reverse pitch it goes into, and the more throttle or RPM speed or power it's going to give the engine. And that's kind of how you power into the beta range. So it actually works that way. Instead of having to grab one hand on the prop levers and pull them back into beta and then add throttle, it doesn't work that way. You just grab these. Weight on wheels opens up the switch, and the further back you pull those two, the higher the RPM is going to go and the more thrust you're going to get going backwards. So that's.
In like an oral practical scenario with the FAA, are they going to get into specifics like with the Hamilton standard, Macaulay, Hartzell, or is it just like a basic overview?
Okay, so it depends if you're talking oral practical. On the oral part, you are going to have to know your basics. I don't think they're going to say anything. No, I don't think I did this. There were no questions that would specifically say on a Hartzell prop. I do think there was some that would definitely say on a hydromatic, a Hamilton hydromatic. So there was nothing about the difference between a Macaulay and a Hartzell, but you would get specific questions about the Hamilton standard 2 position or the hydromatic prop, because they operate so differently. So a typical question would be though, gosh, and I should pull up. Well, it's break time. You guys probably want to go pee or something. So anyway, I'll answer that when we come back. I'll pull up some stuff, and that's what happens when you hit a deer. And I don't know what that is. That's just what happens when airplanes party. All right, so go take a break, and I'll see you in a little bit.